adding vectors and multiplying them by scalars is fairly simple. When you add a vector, you simply add the respective entries of the vector. And when you multiply a vector by a scalar, you multiply all of the entries of the vector by the scalar. However, we don't really have a notion of multiplying vectors together. However, there are other operations that substitute for what is missing here. One of these things is called the dot product. The formula for the dot product in 2 dimensions is the magnitude of A times the magnitude of B times cosine of theta, where theta is the angle between A and B if you were to have them start at the same point. So we kind of read this as A dot B equals length of A times length of B times cosine of theta. But what does this really mean? Like, why would we care about this being a formula in the first place? Well, let's try to get a sense of where the cosine of theta comes into play. So if we look at this diagram here, we have our theta being the angle between A and B. And from here, let's construct a right triangle. So this line that connects these two tips of the vector will not necessarily form a right angle. So we'll have to choose something that creates a right angle. We see that this B vector is a little short, and so if we bring a line down here, we can form a right angle by having this point fall beyond where B is. So we have the cosine of theta is equal to this full length divided by A, which means that this length here is equal to the magnitude of A times the cosine of theta. And so this length here is called the projection. It's the projection of the vector A onto the direction of the vector B. And the reason we write it, the reason it's called this, and this is special, is because now A is uniquely written as a vector that is parallel to B plus a vector that is perpendicular to B. In the standard basis, right, we have a vector that's parallel to the x-axis plus a vector that's parallel to the y-axis. But really, we could have chosen any vector to start with. And so if we have 2 vectors, we can have one vector and we can project it onto the other. Similarly, we can project B onto A using a similar method. So the magnitude of A times cosine of theta is the magnitude of the projection. And we can call this the projection of the vector A onto the direction of B. And so we not only want the magnitude, but we want to write this as a vector, right? Because we could easily write a vector that starts from here and ends here. And similarly, write the perpendicular vector up there as follows. So the projection vector has a magnitude of A cosine theta. So we'll write that here. And then it's in the same direction as our vector B. So we can write B. But this will make it too big, or maybe too small. So we want it to be a unit vector, a vector with magnitude 1 in that direction. And so to make a unit vector, you simply divide by the magnitude of that vector. So we have A times cosine of theta times our vector B over the magnitude of B. So if you look here, the magnitude of A, the cosine of theta, and the magnitude of B are all scalars, whereas this B just by itself is a vector. So we have our vector B, and we're scaling it by this amount. However, sometimes we don't know the angle between vectors. That might be annoying to calculate. So can we write this formula in a way that does not require having a cosine term in there? So we know that A dot B is equal to magnitude of A times magnitude of B times cosine of theta. And so if we were to divide by magnitude of b on both sides, like follows, we would be left with a dot b over the magnitude of b is equal to the magnitude of a times the cosine of theta. So up here, instead of our magnitude of a cosine of theta, we can simply write a dot b over the magnitude of b. So we have a dot b divided by the magnitude of b. And then we also have our magnitude of b in the denominator already, so we square that. And then we multiply by our vector b. And this is the way that using dot products, we can describe the projection of A onto B.